Hello everyone. This is Christiana here. I want to go over this problem on laws and motion. Okay, so if you look at this picture right here, right, you basically have a mass, right, that's holding on to two strings or two ropes, whatever you want to refer to them as. But the important thing to note about this picture is that there is no acceleration, there is no movement, right? So this is basically at rest, you could say. So this type of problem is a two-dimensional equilibrium problem, right? The reason why it's two-dimensional is that if you notice that the tension over here is a vector that needs to be decomposed. Okay, so here's the information we were given, right? So we need to basically find, oops, we need to find the tension 1 and tension 2, okay, given this piece of information. So what I've done before starting this video is I've went ahead and wrote some things ahead of time, but I will still walk you through each step. Okay, because we know we're not going to have motion, meaning this mass is at rest, then we know the sum of all our forces. Since this is two-dimensional, right, we're using the second law of motion, which states that the sum of all forces will equal the mass times the acceleration, right? So since we're dealing with two-dimensional motion, we need to consider both the y and x components, right? So the sum of so being that being that there will be no movement, that means our acceleration is zero, right? When this side is zero, then that means the entire thing on this side will be zero, right? So that just means the sum of all our forces for both the y and the x will be zero, right? That will be very important as we go on. Okay, so let's go on over here. So what I've done here is I've basically translated this picture that we were given. I've translated it to a grid, right? You can move this down here. It's still the same triangle. It's just like a different way to look at it, right? It may be easier for you to visualize it this way or this way, whichever one works for you. But I will be walking with both ways just to make sure I cover all ground. Okay, so if you've noticed, I put the information we were given on this side just to make sure we keep up with that. Okay, so what you're going to notice here is that we're given an angle as well, right? This angle is an angle relative to y, right? So that's why we put alpha, right? And then we have theta, right? Theta is our angle relative to the x-axis, right? And an important note to make here is that alpha and theta will equal 90 degrees. This will also be useful for us. Okay, another thing you want to do is to label your hypotenuse, which is your L, right, and your x-axis, which is your B, right? You can see that those are written up here as well. Okay, so once you've labeled that, it kind of puts things in perspective. Okay, so there's multiple ways you can go about doing this, right? But the first thing you want to note is that whenever you have a law of motion problem, right, you want to basically, and you have a mass, right, you have a mass pulling down on something, you want to, the first thing you may want to do if you're really confused and you really don't know where to start is to find the mg. That's usually an information that you have, right? If you have the mass, right? Because the mg can be written a number of ways. It's can be weight. It can be written as weight, g, or mg. They're all the same thing, right? Okay, so that is just mass times gravity, right? Whatever your mass is, multiply it by 9.8. Sometimes 9.8 rounded to 10. Okay, so the first thing we should do here is realize that, since our mass is 3, then our weight or our mg will be 3 times 9.8. That is approximately 29.4 newtons. Okay, so after you've established that, you have your mg, right? Your weight. If you notice here, so I'm gonna go back and forth between the original picture and what I've derived here. Okay, so if you've noticed here, this T2 is not a vector that needs to be decomposed. However, T1 is, right? So if you decompose T1, right, this will be T1x, and this will be T1y. Okay, what do you notice exactly? Okay, so if you don't see it right away, if you don't see some things right away, you want to draw what's called a free body diagram. Okay, so what I'm going to do is I'm going to draw this as a free body diagram. So bear with me here. Okay, so let's say our weight, our object, right? What forces does it have on it? This is just like a diagram to kind of like put everything together, to see how everything fits together. Okay, as we can see, it has its weight pulling on it, right? You can write that as W or G or mg. I prefer mg. Okay, what else do we know? What else do we know? We know that it has T2, the tension 2, pulling this direction. So I'll put T2. Okay, and what else do we see? The force acting on it. We see T1. T1 is pulling, I'll put T1 in green. T1 is pulling in this direction. That kind of want it to be a little more slanted. So T1 is pulling in this direction. However, it's better to decompose T1 so that it's easier to kind of visualize, what you're working with. So actually T2 is going the opposite direction. I kind of drew it. So I guess we should put T2 on this side. Because if you go back to that picture, T2 is going to the right. Okay, so let's go ahead and decompose T1. Let me label T1. Let's decompose that. So this will be my T1x, and then this will be my T1y. Okay, so what you want to understand is that, like I said before, this is a two-dimensional equilibrium problem, right? Meaning all the forces on the y and all the forces on the x will equal 0, meaning they're going to cancel out. They're going to be of equal magnitude but different opposite directions. That's what it means to cancel out. So what you want to notice here is that, I don't know, let's use uh let's use red for y. What you want to notice here is that your T1y, sorry, T1y is going opposite direction to your mg, right? So what that means is that your T1y should equal your mg in magnitude, but opposite in direction, because the sum of their forces will equal 0. Okay, this is on your y axis. So now on your x axis, you have, let me use orange, you have T1x and T2 going on opposite direction, right? And because we know this is an equilibrium problem, meaning there is no acceleration, that means those two should be equal in magnitude but opposite in direction. So what you want to do for that is put T1x equals T2, right? So this will really help. Okay, so from this point, we still understand, right? We still understand that what we're trying to find is, according to the problem, what we're trying to find is T1 and T2. Okay, so let's see what information we can derive from what we have right now. Okay, so we have mg, right? Because our mg is this right here, right? If we multiply the mass times the gravity. Okay, so you can either leave it as mg or just put the number to help you put things in perspective. Okay, equals T1y. Instead of writing T1y, what you may want to do is say T1 sine of theta. And notice that I put theta here, right? Although in the original picture we were given alpha. And recall that I say alpha plus theta will equal 90. Okay? So when we go on to find theta later on, right? We'll have to use these two lengths that we were given, the hypotenuse and the adjacent of theta. But let's wait on that for now. Okay, so we know that T1 sine theta will give us 29.4, right? So if you can see here, what that means is, if we can get theta, right? If we can get theta, then we will know theta, we will know this, and we will be able to find T1. And after we find T1, we'll be able to use it here in order to find T2. Okay? So let's go ahead and find theta. Okay, so I'm going to redraw the triangle over here so that we can reference it, right? Okay, so we have theta, and then we have alpha, and then we're given that L, or length. You can use any letter for this, by the way. It's just what was given to us in the problem, 0.5 meters, right? And then we add that B is 0.4 meters, right? So what you notice here is that in order to find theta, see, you can use alpha as well, but honestly, I believe it's better to stick with theta, right? But I will show you how to do it both ways if you want to use the alpha instead. But yeah, so let me first let me first discuss how to find theta. So if you look at theta, this is the hypotenuse in reference to theta. This is the hypotenuse, and in reference to theta, this is the adjacent, right? And if you remember, okay, oh, I don't know why I'm erasing that. Let me just put it again. Hypotenuse and adjacent, right? If you remember, we had SOHCAHTOA, right? So since we have adjacent and hypotenuse, what you'll notice here is that this is what we'll have to use. This represents sine, cosine, and tangent. So cosine is what we want to use. So what you want to do is put cosine theta equals, so when you have SOHCAHTOA, this means cosine equals adjacent over hypotenuse, right? So let's go ahead and plug what we have in. Adjacent, right, is 0.4. And then, or you can say, okay, let me just go step by step. Adjacent is B, right here. And then hypotenuse is L, right? So cosine theta equals B over L, or you can say 0.4 over 0.5, right? And in order to find your theta, you'll need to get the arc cosine or inverse cosine of B over L, or 0.5 over 0.4 over 0.5. So let me, oh man, I don't have my calculator here with me. Let's see. So from what I remember, theta will be about 37 degrees. Okay? So now that you have theta, you can find out a lot of things. So let's highlight that in yellow. So if you're working with, instead of theta, you're working with alpha, what you want to understand is that, like I said before, your alpha, where did I put that? Okay, yeah, right here. Your alpha plus your theta should give you 90. Okay, because they're complementary. So if you subtract 90 from 37, you should get 53. This represents your alpha, if that's the angle that you want to use. But for this video, I will be using theta because it's more standard and it's more straightforward. Okay, so theta, we found that is 37 degrees. So now we can plug in theta back into the equation. Into the equation, right? So if I say T1 sine, now that we know theta is 37, I'll put that equals 29.4, right? In order for me to find T1, then I will divide by sine theta, or sine 37. And what I will find is that T1 is about 48.9 newtons, or you can put about 15 newtons, but I'll stick with 48.9 newtons. Okay, so after you find your T1, right, you will see that you'll be able to find your T2, right? Because we determined from our free body diagram that T1x equals T2, right? So you want to go ahead and expand your T1x to be T1 cosine of theta equals T2. Okay? So remember, sine goes with y and cosine goes with x. And this is the reason why I'm using theta instead of alpha. If you were using alpha, you would have to switch those two things. So if you want to just keep your life simple, you can use theta. Okay, so let's go back to the question. So now that we know T1 and we know theta, we can find T2, as you can see. So I can plug in T1, 48.9, right? Cosine of theta, which is 37, equals T2. When you put that into the calculator, you should get about 39.1 newtons, or about 40 newtons. Okay, so that is how I was able to solve this problem. If you have any questions regarding this, or you have another question that you want me to go over, you can let me know. I really hope you have a wonderful day. Thank you.